we're going to define a whole bunch of notation. So remember when we started this course, we started by talking about statements, and then we had little things for connecting statements together. Well, this is going to be kind of similar. We're going to have things for connecting different sets together. So let A and B be sets. So one thing you can do with two sets is you can kind of merge them together into a bigger set, right? You can take all the things that are in the first set, the second set, and just kind of put them all together in one big set. So that's the concept of a union. So the union of A and B is the set containing, well, actually maybe I can just write the set. So it's the set of all x such that x is in A or x is in B. And the notation for this is A with a kind of like a U, but not like this kind of U, but just just like a cup kind of thing, and then B. So when you read this, you should read this as like A union B. So is this definition clear? It's you just take all the things that are in A, all the things that are in B, you put them together in one big set, and it's called A union B. And then there's a similar thing where you take, essentially you take this OR and you make it an and we call that the intersection. So the intersection of A and B is the set of all x such that x is in A and x is in B. And this one's called, or this one is, the notation is similar, except it's upside down. So it's A with a kind of, upside down union sign, B, and you can read this as like intersect. So the set A intersect B is the things that are in A and B simultaneously. By the way, all of this stuff it might sound new, but later in this lecture, we're going to realize that actually you've kind of seen all this notation before when we're doing statements, even if you don't realize it. Okay, so let's just continue with definitions. So the set difference of A and B is the set x such that x is in A and x is not in B. I'm not sure if I formally introduced this notation of crossing something out, but you should just think of this as, as meaning is not an element of. Or you could think of, so writing x not in B is equivalent to writing not x in B. It's just slightly less cumbersome to just cross out the element sign rather than putting things in brackets and writing a negation. But it means the same thing. And here the notation is A backslash B. Okay. So you should think of this as like you take the things that are in A, right, and you kind of cut out the things that are in B. So it's the things that are in A which are not in B. Now we have something called the symmetric difference. I know this is a lot of definitions, but hopefully each of them, I think each of them individually is not too hard to grasp, right? But maybe remembering all of them at the same time is kind of difficult. Okay, so the symmetric difference of A and B is the set. Well, it's the set. So we can write this using our previous notation. I can write the symmetric difference as A minus B. So actually, in words, what you would say here is minus. I should also say that some people write, like some mathematicians, you might see this in certain textbooks and things like that. So some people will, instead of writing the backslash, they'll literally write A minus B with a minus sign. So this means the same thing as that. You probably won't see this notation, but I'm just writing that in case you Google something that and you see A minus B and you're confused or something. You know, some people write that for this. But so the symmetric difference is A minus B union B minus A. And the notation is A with a plus sign with a circle around it, and then B. But again, this is like not universal notation. So some people write this with a triangle, A triangle B. But for the purposes of this course, we always write it with a plus. But some people might write like A triangle B. So if you see that somewhere in a textbook or on the internet, don't be too confused. But yeah, our main notation is A plus B, like with a circle. Okay, let's, I'm going to do one more, well, yeah, kind of one more little bit of notation here. So often when we're dealing with sets, there's sometimes like some sort of universe that we're thinking about that this set is contained in, right? So if I take the numbers 1, 3, 7, you know, that set, you could think of that as like a subset of the universe, which is the real numbers. Or you could think of it as a subset of the universe, which is like the natural numbers or integers or whatever. So, so given a universe, so the reason I'm talking about universes is that this definition only makes sense if there's some universe involved. Given some universe U such that A is a subset of U, the complement of A, you know, so often we'll just like, if we kind of understand what the universe is, then it makes sense to just write the complement of A and not have any more explanation. But just for clarity here, really this is always the complement in that particular universe. So it depends on the universe as well. And it's all the things in the universe which are not in A. So it's U minus A. And here the notation is, we often write like AC. So, right, and you should read this as like the complement of A. Okay. But just to be clear, the notation AC, like A complement, or you can also say it's just as A complement. Like, if nobody has specified any sort of universe, this definition, this notation by itself doesn't really make any sense, right? Because if I have what is the complement of 1, 3, 7? Well, it depends what the universe we're dealing with is, right? If it's the integers, then it's all the integers not in this set. If it's the reals, then it's all the real numbers not in this set, right? Okay. So let's try to understand these, all of these definitions with a sort of picture. So imagine this rectangle is a sort of universe of elements. So this rectangle is U, the universe. Let's say that everything inside of this circle is the elements of A. Everything inside this circle is the elements of B. Okay. And there's some elements in both of them and some elements which are in neither of them, etc. So this breaks up the universe into kind of 4 regions. I've got this region, that one, and the 4th region is the outside of A and B. Okay. So which regions, so if I take the set A union B, which regions does that give me? Or so I guess I mean, yeah, well, it will definitely give me 2, but does it give me more than that? So union is a set of all x such that x is in A or x is in B, right? Yeah. So the union is going to give me all 3 regions. So I don't know where to write this, but A union B is regions 1, 2, and 3, right? How about A intersect B? Yeah, exactly. So, right, so unions are very inclusive, right? A union puts together all the things that are in A or B, right? But an intersection says only the things that are in A and in B, right? Which is which is just this stuff in region 2, right? This stuff here is in A, but it's not in B, whereas this stuff is in B, but not in A, so it's region 2. What about the set difference of A and B?
1.
Yep. Right? Because it's basically this, you should think of it as like take all of A and then cut out the stuff that's also in B. So when you cut that out, it'll be cut out the stuff in 2, so it's just the stuff in 1. This one's maybe a bit trickier, I don't know, but the symmetric difference, I know it's not on the board anymore, but yeah. Are we in agreement? 1 and 3, right? Because, right, it's the stuff that's in A but not in B, and then you put that together with the stuff that's in B, not in A. So it's going to give you, this and this, but it doesn't give you this stuff. What about A complement? So let's, on the count of 3, say what you think is the answer. So 1, 2, 3. So some people maybe know the answer, but there's a little mumbling. I think I heard some numbers which were not quite correct as well. So, right, the complement is the stuff in the universe that's not in A. So it's definitely not this. It's not region 1. It doesn't have region 2. But region 3 is fine because that's not in A. And region 4 is also fine. So this is regions 3 and 4. Okay. It's all the stuff that's not in A. Okay. By the way, do people know the name of this kind of picture? Yeah, totally. So these are going to come back in the course a few times, but yeah, this is a Venn diagram. Okay. Yeah, I would recommend really getting kind of internalizing these definitions. In the same way, when we did logical connectives, it was. I mean, I guess everyone would agree, right? It was super important to know what these little ands, ors, implications mean, right? Oops. This is really, yeah, the same level of importance. But here's the good news. If you understood the logical connectives, then this is actually pretty easy to remember. So really, the symbols kind of tell you what these things mean if you already know logical connectives. Because union, or maybe I'll write it this way. So I'll write logical connective or, it's kind of like union. I mean, it looks kind of the same, right? Except one's curvier than the other. And look at, we've got this word or sitting right here, right? Union is the set of all points which are in A or in B, or, right? So I could have actually written this as the x such that x is in A or x is in B, right? And this is not a mistake. The notation was developed so that these things have this connection, right? And and is like intersection, right? There's an and sitting right in the definition. So an element is in A intersect B if it's in A and it's in B, right? So these things kind of connect. What about, okay, there's not going to really be any version of implies or anything like that. But how about complement? So in terms of logic, like what do you think that corresponds to? Yeah, definitely, yeah. So the complement is kind of like negation, right? A complement is kind of like not P when we had statements P, right? Because you know, it's all the things. I mean, you could literally write a complement as the set of all x such that, well, x in the universe. So that's one weird thing about the set thing is you need a universe, but such that it's not true that x is in A. Or in other words, x is not in A. You can write it this way too, but, right? So complement is like the same thing as negation. How about, remember contradictions and tautologies? Can anyone think of like what might be the set equivalent of a contradiction or a tautology? Or let's say just contradiction. That's maybe a bit weird, but any thoughts? Well, maybe we'll come back to that. Let's come back to that. It might become clear later. So keep thinking about what these might be. So the point of making this, part of the point of making this connection is to help you remember these symbols and what they mean. The other part of it is to tell you that, well, you remember all these laws of logic. Well, there's a whole thing called in the notes called laws of set theory, but it's the same stuff, except what you do is you replace ors with unions, ands with intersections. Oh, I've kind of got these on the wrong side, don't I? But you replace negations with complements. So let me see if I can get you to guess what the laws of logic are. Or sorry, the laws of set theory. Based on what you already know from logic. And maybe this will test how well you remember these laws of logic as well. So laws of set theory. So let's talk about commutativity. So what should that, so okay, if you remember the laws of logic, usually there's like two versions of most of these laws. But can anyone tell me even one version of this, but what should it be for sets? Like what should the commutativity law be for sets? Yeah, exactly, yeah. Commutativity was this thing. So I do recognize that probably a lot of people have already forgotten what it meant, what these laws of logic are, but this is good to remember, right? This is, you know, commutativity said if I have like P or Q, that's logically equivalent to Q or P. And for sets, it's the same thing, right? A union B is the same as B union A. It just says you can swap the two sides. And actually, if you think about the definition of union, like the reason this is true is because, remember, union has like an or in the definition. By commutativity of or, you could switch that or around, and then that kind of switches the union around. So it's kind of, these are kind of the same thing. And then you also have the same thing for intersection. A intersect B is B intersect A. And the analog in logic, like the associated law is P and Q is the same as Q and P. Okay. So you see how you can kind of probably guess most of these laws of logic, or sorry, laws of set theory. Half the time I'll probably say the wrong thing, but how about associativity? So I feel like this is one we didn't use that often in logic, but yeah, it is one of these laws of logic. Yeah, what should that be for sets? Any thoughts? So associativity was this statement that like P or Q, it's this thing about brackets. So if I take P or Q or R, that's the same as P or Q or R, with the brackets this way or the brackets that way, right? So for sets, it just says A union B union C is the same as A union B union C with the brackets in the other place. By the way, it's also kind of clear here, like equals is now like set, like for sets, the equal sign is now the same thing as our logical equivalence was for statements. And then you have the similar thing for intersection. A intersect B intersect C is equal to A intersect B intersect C. If you didn't remember this law, I kind of understand because we didn't use it very often. I mean, it's kind of just obvious, right? But how about distributivity? So again, all of these like laws come in pairs, but can anyone tell me what distributivity should be for sets? Yes, thank you. Right, so it's that thing where if you have like a bracketed thing, kind of like before with associativity, except where you have different connectives, then what you can do is it's kind of like when you have an equation or a thing like, you know, x times y plus z, you can kind of bring the x inside. So this is like you kind of bring the A union inside, and you kind of put it like that. And then we have a kind of, and yeah, this is exactly the same as with logic. Yep. Ooh, thank you. Yeah. Thank you. Indeed, yeah. So this A should go on the B, and it should go on the C, and there's an intersect between them. And then you have a second distributivity law, which is the same, but everything is upside down, like all the connectives are upside down. So A intersect B union A intersect C. And really, all these laws so far, they just follow from the same laws with and or, because you can just use the definition of union and intersection and use the ands and ors and apply the laws of logic to them. And this should work. What else do we have? Well, here's a good one. How about De Morgan? Again, of course, there's two of them, but De Morgan for sets. Any thoughts? Remember what De Morgan was for, right? De Morgan was like this thing. When you have a not outside of a or an and, you switch the sign, you switch the connective, and you negate both sides, right? So what should that be for sets? So okay, probably we can kind of tell, remember, or is like union, so probably it's like some kind of a negating a union, but what does negating mean, right? And like I said, negating is like taking complements. So if I take A union B and take the complement of the whole thing, so this is, again, assuming A and B come from some universe, some common universe, then this is going to be A complement intersect B complement. And similarly, if I take the complement of an intersection, then it's the union of the complements. If you sort of think about this, like in terms of the Venn diagram, you know, think about which regions A intersect B makes, what's the complement of those regions, and then think about the complement of A union the complement of B, which regions are those. You can see it's actually the same thing. So like these are really equal. But is that one okay? Any questions? Okay. How about this double complement? So double complement is like double negation. So if I take A complement, that's equal to A. Right? And that's analogous to like the not P, not P is logically equivalent to P, right? If you complement and then you complement, you get back to the same set. So this is, I think, most of the laws of logic, maybe not all of them, but basically the message here is every law of logic, I think every single one of them, has a relationship to, like it has a corresponding law of set theory. You just change the ors to unions, the ands to intersections. But there was a bunch of other laws involving tautologies and contradictions, right? So let's come back to that question. So in relation to laws of logic, okay? Okay, remember we had, for example, some kind of a thing which said P or contradiction is the same as P, for example. And P and tautology is the same as P. Like, these were two laws of logic. Kind of with that in mind, like, does anyone have an idea of what's the set theory equivalent of the contradiction? Yep, exactly, yeah, that's what I'm looking for here, the empty set. How about the tautology? That one's maybe a bit weird, but yeah. Exactly, yeah. So of course this like requires there to be a universe that, yeah, makes sense, but like, yeah, it's the universe. Okay, so if we kind of think of these definitions, this kind of makes sense, because if I take, so there's these, I think this rule is called identity, like these two things here. And the kind of version of that in set theory would be A union, the empty set, is equal to A, or A intersect the universe is also equal to A. Which makes sense. If I have a set and I union it with nothing, then it stays the same. It's the same set, right? If I intersect it with everything, then it's again the same set. You know, I haven't lost anything from that or gained anything. Okay. And then there's these dominance rules. So if I take, so here, if I take A intersect the empty set, I just get the empty set. If I take A union the universe, I get the universe. Oh, maybe there's one I missed. Idempotence. Does anyone remember this? What's idempotence for? Exactly, yeah. And also A intersect A is A, yeah. This comes from these rules we had, which were like P or P is logically equivalent to P, and P and P is logically equivalent to P. Okay, any questions about any of these? So it might feel like a whole bunch of new stuff to memorize, but yeah, I want to kind of communicate the fact that you already kind of know all of this. So you should be able to make if you remember your laws of logic, you should hopefully be able to make the translation from one to the other. Okay. I should say, we also had all these other, so if you remember, there's like a list of logical equivalences. Some of them were called laws of logic. And then there was other stuff like doing contrapositive and, you know, implication things and biconditional things. Technically, those are not called the laws of logic. So basically, all I'm claiming here is that everything with and or, like if you have something that's written with and or, you can translate that to set theory. But there's not a very good like analog of the or kind of translation of like implication or something like that. So yeah, the implication thing doesn't really translate, but the ands and ors translate, and negation translates over.